Some of the solids we encounter in everyday life have a crystalline structure. For example, when you freeze water, the most familiar liquid around, it becomes ice, which has a crystalline structure. Another familiar solid is salt. It has a also crystalline structure. Additionally, most metals have a crystalline structure. Among them, polonium has the simplest cubic crystal structure. Are there any classical mechanics features that can be observed in these crystal structures? Another question is about elastic waves. For example, seismic waves and sound waves can be elastic waves in a solid medium. How do elastic waves propagate, reflect, and refract, and what is their relationship to crystals? In this video, I explore the propagation of elastic waves, along with a model of the mechanics of the simplest crystal. The simplest crystal structure is the primitive cubic structure. Once we have a crystal structure, we also need to consider the interactions between the particles. For simplicity, let's say they are connected by springs have quadratic potential. Now that we have a well-defined system, let's write the equations of motion. In one dimension, a particle is connected to two particles to the right and the left. In two dimensions, four particles to the right, left, top, and bottom. And in three dimensions, six particles to the front, back, top, bottom, right, and left. Therefore, the forces from two particles per dimension must be included in the equation of motion. If we include them, the equation looks like this. What do we get from this equation? Let's look at the simplest case, one dimension. In one dimension, the equation can be written simply like this. Before we get any information directly from the equation, let's look at how a system satisfying this equation behaves. Even if we don't find the solution directly, we can approximate it numerically. Let's simulate it based on the equations of motion. Nothing would happen if we just left it still, so let's fix the right end and hit the left end. The particle at the left end will instantaneously acquire the impact P, compress the spring, and continue to transmit the wave to the right. Did you see that? Let's slow down time and observe it again. As the wave reaches the fixed right end, it reflects and returns. It's too hard to see. Let's draw the graph of the particle's displacement on the vertical axis. Now we can see the propagation of the wave on a one-dimensional lattice. Now let's look at some interesting examples that we can think about intuitively. The first is the propagation of a sine wave. If we simulate the initial displacement and initial momentum of a particle as a trigonometric function like this, we get a sine wave propagating to the right or left. Each sine wave has a different wavelength, but similar speeds. Another form of wave that we learned in the general physics course is the standing wave. If the initial conditions are set well to generate standing waves, we can see standing waves like this. Next, let's look at the Gaussian pulse, which is often used in wave examples. Let's take a Gaussian pulse traveling in the right direction. Fix the right end and let time pass. The pulse will flip and come back. This time, let's leave the right end free and send a pulse. As expected, it reflects right back without flipping. Now, let's look at the wave packets traveling in different directions, which often appear as the linear superpositions of waves. The result is this: they ignore each other and propagate. As you can see, we were able to observe many of the properties we learned about waves from the simulation. Next, let's try to analyze the equations directly. For a system connected by a spring with a quadratic potential like this, it is useful to find and analyze the eigenvibration modes. Depending on whether the ends are fixed or not, the potential matrices are determined like these, and by diagonalizing them, eigenmodes can be found. Actually, taking some eigenmodes and visualizing them, we can see that they oscillate in the form of standing waves with different frequencies and different wavelengths. Under the condition that both ends of the lattice vibrate identically, these sine waves are eigenmodes. One interesting thing is that the frequencies that can form a sine wave are discrete, not continuous. Finally, let's derive the wave equation from the equations of motion of the lattice. First, let's substitute the displacement of the object, then the equation becomes like this. And manipulate the right-hand side. Finally, obtain the wave equation through the limit where the number of particles becomes infinitely large and the interparticle spacing becomes short enough. From this process and the limit, we obtained the wave equation from the equations of motion of the lattice. To summarize, in this video, I introduced a simple model describing crystalline solid and elastic waves, found the equations of motion, conducted numerical simulations, found some eigenvibration modes, and obtained the wave equation from the equations of motion of the lattice.